Are you ready? All right, here's what we got to do. We now have to make a calculation table. We had a data table, and I had that up on the board, and I kept the first trial data table up here because I am going to go through a sample of data with you for the trial number 1 to show you what to do to fill in your calculation table. So your calculation table should look like this. I put it up here in green marker. Now the calculation table is roughly put together down here for you at the bottom of the first page, but it just doesn't have room, so I left out these two here. So you want to complete the calculation table, bump, and on my sheet it goes to here, but you do want to add these last two columns, the centripetal force calculation giving you the experimental value and the percent error column. So add those in to the table down here at the bottom. Now this is just example data. I just made this stuff up to show you example data. That's not data that we had. That is not, I repeat, this is not any of our data for the lab. It was just example data going in to put it so you can see what it would look like. Okay, so now what we want to do, once you have your data table complete, and this is for all 7 trials, there's a lot, I'm sorry, the calculation table. The data table had a lot, and the calculation table has a lot. You have to do a lot of number crunching in this lab, much more so than any other lab we have for the course. This is a number crunch, data intensive, calculation intensive lab. Lots of stuff to do here. So let's dive in. There are 2 labs which are the most difficult for students to get done in terms of doing them right and getting good scores on. One's the vector lab. And some of you, if you go and you look at your vector lab scores, for many of you, that's your lowest lab grade. This one is also a little challenging, but if you just follow the step-by-step, then hopefully it turns out to be just a lot of number crunching and not challenging to get the numbers that we should get with the data we have. Okay, so let's get started. Let's turn over to the back side. All right, there we go, second page. Now, sometimes students ask me, why did you circle these 2? Are those the only 2 that we have to do for calculations? No. I circled those 2 for the reason that we're going to use those for the percent error. So we have to do all the calculation setups here. Now, each one of these calculations, you have to do each one of these 5 calculations, 6, so I didn't see that there. 6 calculations. 1, 2, 3, 4, 5, 6. Yes, they correspond to our calculation table. And when we do a calculation, we'll put it in the table. This has to occur for all 7 trials. 1, 2, 3, 4, 5, 6, 7. Right? 7 trials. So that means altogether, you're going to number crunch 7 trials times 6 calculations for each trial. We all know 6 times 7. Come on, remember 3rd grade multiplication tables. 42 numbers you have to calculate. Now, a lot of these are done the same way, so it is kind of repetitive, and they're not hard calculations, but let's go through some data and show you how it works. Okay, calculation number 1. Calculate the weight of the hanging mass and enter it in the table as centripetal force. So each one of these calculations corresponds to the spot on the table. This is calculation number 1. This is calculation number 2. Calculation number 3. Calculation number 4. So as we go down, 1, 2, 3, 4, we'll put the answer in these spots. Calculation number 5. And calculation number 6. So each calculation on here, you take that number, calculate it, and put it in the corresponding table spot. Okay, so let's do the first one. Calculate the weight of the hanging mass. The weight of the hanging mass. And it says right here, you know that weight is equal to mass times gravity. So what we do is we take the weight of the hanging mass. So from our data table, for trial 1, the hanging mass was 0.1 kilograms. Multiply that by 9.8. So do that out. 0.1 times 9.8. You can get an answer and put it right there. Should be 0.98. 0.98. Okay. All right. Now, and everybody will get these to be the same. What you're going to get different than somebody else in the class potentially is the times, because you know you did the 1, 2, 3 and stopping. Okay, you did that, and it's gonna be a little different than somebody else. Okay, reaction time and what you saw or heard and reaction time, a little different. Hopefully, your times would be plus or minus a half a second from somebody else or from me if I were doing it, hopefully. Okay, but, you know, that's part of the error. Okay, how do we get this trial 2 calculation? Okay, trial 2 calculation, you take the time that you got for your trial 1 and divide it by 20, because we want the time of 1 revolution. Okay, we want the time of 1 revolution. So if you take this time and divide it by 20 revolutions, it gives you the amount of time for 1 revolution. Now what I did is I went and I watched that video, and I came out with the time. Okay, I watched myself do this and listened, and I came out with a time of 14.2 seconds for trial 1. So I wrote that down here, 14.2. Actually, I got a 14.15 if I remember right, 14.15, and I rounded it to 14.2. Some of you might got a little less than that, some of you might got a little more. And what I was watching, and this is going to be part of the error. Part of the error is when I said go and I said stop, you know, if you're listening to my voice and doing it, that might have a little different time than when I was actually watching, and I caught this with myself. Ray said go, and I started. When I saw the stopper in the video, I started when you said go, and then I watched it go around 20 times. It was at the exact spot again. I hit stop. And it actually came out to be a little different than my voice. All right, some error there, potential error. That's what happens as part of the lab. Maybe you want to do these times multiple times and see what you get for an average. I did it out watching the stopper, and I came out with 14.1. So I'm using 14.2 for my example. Now that's the total time, 14.2. There's a 14.2 divided by 20. Okay, that's what you do. This is trial 2, and it tells you this right here. Find the period. Take the total amount of numbers of revolutions divided by 20. So period is equal to time, 14.2, divided by 20 revolutions. And we got 0.71. So the time period for my data, and you'll use your data. If you've got a different time, then use your time. You don't have to use my time. Use your time. But I'm using this to show the first example. Okay? Again, it might be a little different than yours. Circumference is around a circle is 2 pi r. Remember that 2 pi radius, right? So 2 times pi. I use 3.14 for pi. Double it, 6.28. So 6.28 times the radius for trial 1, 0.75. So times 0.75, enter. Now you get 4.71 meters is the circumference, the distance around the circle. Okay, how fast is that velocity traveling in meters per second? Well, velocity is, without accelerating, we're just going at a constant speed. I mean, technically, when you go in a circle, you are accelerating because you're changing velocity, but we won't get into that. Sorry, I'll move on. So we're going to take our speed, which we have here, our velocity, our distance divided by time to get our speed. So our velocity is distance over time. So velocity is distance over time. And we're maintaining a nice steady speed. So that distance is 4.71 and the time is 0.71. So we're going to take circumference and divide it by the time period. Okay, so let's do that. Circumference, 4.71, divided by the time period, 0.71, enter. And I get my velocity going around that circle, 6.63. 6.63. So we'll take that 6.63, put it here. All right, now we're ready for the next step. And it does say step 3, calculate, you calculate circumference by 2 pi r. Okay, step 4. Calculate the experimental centripetal force for each trial. Use the stopper mass. This is a big mistake students make. Use the stopper mass to do this calculation, not the hanging mass. This is hanging mass. This is stopper mass. So to do this calculation 5, 1, 2, 3, 4, 5, we are going to use centripetal force equation. Fc is equal to m e squared over R. Okay, that's our centripetal force equation. So we're going to put our data from our lab in here and calculate what that FC is using the data. So FC is equal to, that's the stopper mass. Stopper mass, okay? Do not put this mass here. No. Put that mass there. 0.0197. 0.0197. All right, got that. I don't know if you can see that. It's kind of small up there. I think you can see that. Well, you can at least know what I'm putting there. And you can do this yourself. That's stopper mass. The velocity, we calculated that in the last calculation. 6.63. 6.63. And we're going to square that. Don't forget that's got to be squared when you do the math. Divided by the radius. The radius is 0.75. 0.75. Now, of course, if you were doing this with trial 4 and 5, you would not use 0.75. Okay, remember that. You would use 0.5 for trial 4 and 1 for trial 5. So be careful of that. 0.75 is used for trials 1, 2, 3, 6, and 7. So you got to be careful and see which trial you're doing. Don't just get into a mindless habit because they change. So be aware of that. Hey, do the math. Let's do the math and see what we get for our experimental FC. All right, so here's how I would do it. 6.63 has got to be squared. So I'll do that first. 6.63 times 6.63. Hit enter. I'm going to multiply that by 0.0197. Hit enter. And then I'll divide by 0.75. Divide by 0.75. Enter. And I come out with 1.15. Okay, 1.15. So our centripetal force is 1.15. And that's a force, so it should be in newtons. And I should have put that here for a unit. This should be, and this is newtons as well. This is newtons. And that's newtons. Okay. So we'll put that up here. If I put that up here in newtons, I don't have to keep repeating it down here. So newtons. All right. So now what about my percent error? Remember how to get percent error. True minus experimental divided by true. Well, what's the true value? Well, going back to why I circled those numbers, 1 and 5, are the ones that you're going to use in this calculation. The true value is this value, column 1. That's your true centripetal force. That centripetal force comes from right here. If we don't have that mass, this is not going in a circle. It's going to take off, right? So if we're twirling this around and somebody comes up and they cut that, takes off. This is the source of our centripetal force. This hanging mass multiplied by 9.8 is the true value. This is our experimental value. So that's what we use. So true minus experimental divided by true multiplied by 100. We'll see what we're going to get. We're going to get about 16%. So 1.15 minus 0.98, doesn't matter what order I do that in, divided by 0.98, multiplied by 100, I get 17.3% error. 17.3. Okay, so that's trial number 1. Now you might get something different because you did not come up with a value of 14.15 or 14.2 seconds. Maybe you got something less, maybe you got something more. Okay, see what you get. Now here's what I tell students. It's a tough lab to do. This is for students to do correctly. This is the hardest lab of the entire course. Yeah, it is. Well, I mean, vectors, I suppose you could say, those are hard. If you're not complete, if you didn't do everything you were supposed to do, then that can be a little hard. But this is just here, that twirly thing, it's hard to do. Not only is it hard to do, there's friction involved, there's drag, there's timing errors. Yeah, there's friction. Because when you're twirling this around, well, that is going around that top like that here. When this is twirling around here, there's friction, there's drag there. And that causes to make this harder for this thing to move correctly. So if this isn't going to move easily, then it's, you can make a mistake by going too fast or too slow. And I don't see the result of that because of that friction. If there's no friction, then that thing is going to move up and down much easier, and we can get a better twirlage, how's that for a word, and we get a better time out of it. Also, the timing could be off, so there are errors here, and it's hard to do this one correctly, and there's nothing you can do about that friction, which is going to cause inherent percent errors. Okay, so I always tell students, if you get under 30%, for all trials, you're doing well. You're really doing well. If you get under 10% for some of the trials, you're doing really well. That was a really good trial. So this is the highest percent error that we have in any of our labs that we do for the semester because of that friction. We can't get rid of it because of the timing errors. What are you going to do, right? Okay, so do these out, see what you come up with percent errors. I did this. I took the liberty of already doing these out. This one I got 10.6 for trial 2, and I got 18.1 for trial 7. So for 10.6, I did that one out. I came out with the percent error there right around like 5 or 6%. So that's like really, really close. And this one here, I came out with the percent error of that one between 25 and 30%. So that one is a little bit off. Now let me give you a little hint. This should be, the time should be 20.0 something seconds. Now you can actually figure out how I figure that out. You can go ahead and figure that yourself and see what these times should be. It should come out to be about 20.0 something seconds. Look, we were off. Well, in my counting, I was off by less than 2 seconds. Now you might say, well, that's not very much, right? 2 seconds. Well, that 2 seconds of being off made a big error. Okay, this will come out to be like 25 to 30%, somewhere in that ballpark of an error. It's a big error. So, and there's, that shows that there's drag there, especially when we had 2 stoppers. 2 stoppers causes more weight. So gravity's trying to pull this down, right? Gravity's trying to pull this down, and that causes more drag here, higher friction. You know that weight causes friction. You know that. So we are going to expect the highest error here. Now I didn't do the other one, so maybe I'm wrong. Maybe I'm wrong on that one. Do them out, see what you come up with, and maybe that's not the highest error. Or maybe the highest error was trial 5, and that one was like all over the place, right? I mean, maybe that one is. Don't know. We'll find out. All right. This is a long explanation because there's a lot of calculating here. These are quick calculations. They're each fast, but you got to do a lot of them. Be aware you're changing radius. Okay, you're changing your radius. Your circumference changes. It's the same for 1, 2, and 3, but for 4 and 5 that'll change. And remember, this is important too. Remember that the mass that you use for the stopper for trial 6 and 7 is different. It's not 0.0197. This is only for the first 5 trials. So be careful with that when you go trial 6 and 7, putting in that mass of the stopper. It's different for those 2. All right, do those out, see what you get. Then